In the rigidly controlled airspace of Soviet frontal aviation during the Cold War, a strike pilot was not considered a tactician. They were, in the most literal sense, a biological actuator for a ground controller located hundreds of miles away. The Sukhoi Su-17, known to NATO as the Fitter, perfectly embodied this philosophy. It was a Mach 1.7 variable geometry strike fighter built with the structural integrity of a main battle tank, capable of carrying over 8,800 pounds of ordnance through intense ground fire. Yet by deliberate design, the engineers in Moscow stripped the pilot of almost all situational awareness. There was no ground mapping radar. There was no tactical display. Instead, the nose of the aircraft was dominated by a massive intake shock cone, and the instrument panel was slaved to a closed-loop radio command system. The pilot flew the aircraft, but a radar operator in a bunker fought the war. This design choice was not an oversight. It was the foundational premise of Soviet air doctrine. The plan assumed a massive, symmetrical conflict on the plains of Europe, where ground-controlled interception GCY stations would mathematically orchestrate the airspace, feeding exact headings, altitudes, and release points directly to the aircraft's instruments. The pilot simply aligned the needles on their dials and squeezed the trigger when commanded. But when this inflexible command architecture collided with the chaotic, decentralized realities of guerrilla warfare and modern combat, the results were disastrous. The rigid umbilical cord connecting the Su-17 to its ground controllers became a fatal flaw, leading directly to catastrophic instances of friendly fire, missed targets, and tactical paralysis. Why would a superpower pour immense resources into designing a highly capable supersonic penetrator only to engineer the pilot's brain out of the loop? The answer lies in a strange intersection of brilliant aerodynamics and deeply flawed military philosophy. If you enjoy detailed deep dives into military engineering and strategy, subscribe to the channel. I've got a lot more planned. To understand why the Su-17 operated this way, you have to look at the severe engineering problem it was originally built to solve. The Su-17 was not a clean sheet design. It was a desperate, highly pragmatic modification of the earlier Su-7, a swept-wing fighter-bomber that possessed excellent low-level speed but was crippled by its own aerodynamics. The Su-7's aggressively swept wings generated very little lift at low speeds, meaning it required incredibly long, perfectly paved runways to get airborne. In a hypothetical European war, NATO's first move would be to crater Warsaw-packed runways. The Su-7 would be grounded on day one. Sukhoi engineers needed an aircraft that could operate from short, improvised airstrips, carry twice the payload of the Su-7, and still dash at supersonic speeds at treetop level. The American solution to this problem, seen in aircraft like the F-111 Aardvark or the F-14 Tomcat, was full variable geometry wings. The entire wing structure pivoted from the fuselage. But the Soviets lacked the lightweight titanium alloys and advanced hydraulic synchronization required to make a massive, full-wing pivot reliable in a rugged, single-engine frontline fighter. Instead, Sukhoi adopted a brilliantly simple, heavily compromised alternative. They took the existing Su-7 fuselage, kept the inner half of the wing bolted firmly in place, and only allowed the outer panels to sweep backward and forward. This approach, pioneered on the Su-17, solved the runway problem almost overnight. With the outer wings swept forward to 28 degrees, the aircraft generated immense low-speed lift, cutting takeoff distances in half. Once airborne, the pilot could actuate hydraulic motors that drove the outer panels back to a sharp 62 degrees in just 12 seconds, turning the aircraft into a low-drag supersonic dart. But this raw aerodynamic solution came with a hidden cost that the armament crews and aerodynamicists had to pay for in blood and sweat. Because only the outer half of the wing moved, the heavy weapons pylons had to be clustered on the fixed inner wing section and the fuselage. While this simplified the fuel plumbing and meant the pylons didn't need complex swiveling mechanisms to stay pointed forward, it concentrated the center of gravity in a very tight box. When a pilot dropped a heavy bomb from one side of the aircraft, the fitter became notoriously unbalanced. The outboard sweep mechanism itself added nearly 900 pounds of dead weight to the airframe, moving the center of mass slightly aft and making the aircraft highly susceptible to departure from controlled flight during aggressive asymmetrical maneuvers. To overcome the weight of the swing wing mechanism and the increased payload demands, the designers needed brute force. They turned to the Lyulka Design Bureau, which provided the massive AL-21 F3 turbojet engine. This power plant was a marvel of raw, unrefined power, generating over 17,000 pounds of dry thrust and an astonishing 24,800 pounds in full afterburner. The AL-21 transformed the Su-17 into a low-level muscle car, capable of accelerating rapidly even while heavily loaded with drag-inducing unguided rocket pods and iron bombs. However, generating that kind of thrust from an early 1970s turbojet meant the engine drank fuel at an alarming rate. The massive fuel consumption created an immediate operational paradox. The swing wings were designed to allow the fitter to carry more weapons, but to get those weapons to a target that was more than a few hundred miles away, the aircraft had to carry massive external drop tanks. These drop tanks took up the very hard points that were supposed to hold the increased weapons payload. To mitigate this, Sukhoi designers began swelling the fuselage, adding prominent dorsal spines behind the cockpit to house additional avionics and fuel cells. The Su-17 grew heavier, bulkier, and more dependent on its massive engine just to stay airborne. This reliance on raw thrust over aerodynamic finesse created a terrifying reality for the pilot during combat maneuvers. The AL-21 engine was notoriously sensitive to disrupted airflow. Because the fitter used a nose intake design, any aggressive high angle of attack maneuver, such as pulling up sharply to avoid a mountain ridge or a surface-to-air missile, blanketed the intake in turbulent air. If the pilot pulled back too hard on the stick, the engine compressor would choke, resulting in a violent compressor stall. In the middle of a combat zone, flying at 200 feet, losing the engine meant an immediate ejection. Pilots learned to fly the fitter smoothly, avoiding high G yanks and respecting the engine's demand for clean, undisturbed air. Stepping away from the raw mechanics of the airframe, the true character of the Su-17 was defined by its cockpit and avionics suite. The front of the fitter was entirely consumed by the engine's air intake. Placed directly in the center of this intake was a translating shock cone. At supersonic speeds, this cone moved forward and backward to perfectly position the supersonic shockwave, slowing the air down to subsonic speeds before it hit the delicate compressor blades of the engine. It was a highly effective thermodynamic solution, but it completely eliminated the possibility of installing a ground mapping radar. Without a radar, the pilot was fundamentally blind to the battlefield geometry. In Western strike aircraft of the same era, such as the American A-7 Corsair II or the later A-10 Warthog, designers prioritized pilot autonomy. The A-7 featured a ground mapping radar, a projected moving map display, and an advanced head-up display HUD that allowed the pilot to locate, identify, and engage targets of opportunity autonomously. The Su-17 pilot had none of this. The cockpit was a cramped, claustrophobic array of analog dials and switches, colored in the standard Soviet turquoise green intended to reduce eye fatigue. Instead of a HUD, early models featured a simple ASP-17 glass gun sight. Instead of a radar, the shock cone housed a CLEN-PS laser rangefinder. This laser was not a targeting pod. It could not search for targets or display an image to the pilot. It simply fired a beam straight ahead to measure the distance to the ground, feeding that data into the rudimentary analog bombing computer to calculate the impact point. Because the aircraft possessed no independent means of finding targets beyond visual range, the pilot was entirely reliant on the Vozduk-1 ground control system. This system was the central nervous system of Soviet frontal aviation. Massive P-35 and P-37 radar arrays positioned safely behind the front lines would track the Su-17. Ground controllers, huddled in dim command vehicles, would calculate the necessary intercept geometry or strike coordinates based on intelligence reports. These controllers would then transmit commands via secure radio or the LeSueur data link system. The Su-17 pilot navigated using the RSBN short-range navigation system, which worked by picking up signals from ground-based beacons. The pilot's job was to watch a small gauge called the NPP, the navigation instrument. When the needles crossed, the pilot turned. When the altitude dial flashed, the pilot descended. They flew at 500 knots 150 feet off the deck, relying entirely on a ground controller who was looking at a two-dimensional radar screen hundreds of miles away. This brings us to the operational reality of flying the Su-17 in combat, which was vastly different from the sterile proving grounds of the Soviet test facilities. The doctrine of ground-controlled strikes worked relatively well in exercises over the flat, carefully mapped plains of Eastern Europe. But when the Soviet Union deployed the Su-17 to Afghanistan in the 1980s, the doctrine immediately fractured. Afghanistan was a war of jagged mountain ranges, deep ravines, and highly mobile guerrilla fighters. The rigid ground control architecture was utterly incompatible with this environment. First, the mountains blocked the line-of-sight radio waves required for the RSBN navigation beacons and the Vozduk-1 data links. When an Su-17 pilot dove into a valley to execute a strike, the communication link frequently severed. Suddenly, the pilot was flying blind at 500 knots in a rocky canyon, relying purely on analog gyroscopes and a paper map marked with a grease pencil. Second, the nature of the targets changed. The Su-17 was designed to hit massive NATO armored columns or fixed bunkers. In Afghanistan, the targets were small bands of insurgents who moved rapidly and blended into the terrain. The ground controllers, sitting at regional air bases, could only provide static map coordinates. By the time the Su-17 arrived over the target area 10 minutes later, the enemy had often moved. Because the pilot had no onboard sensors to verify the target, and because they were traveling far too fast to loiter and search with binoculars, they had to trust the coordinates blindly. Ground commanders would frequently pop colored smoke to mark friendly positions, telling the fast-moving jets to strike a certain distance away from the smoke. But insurgent forces quickly adapted, capturing colored smoke grenades and deploying them simultaneously. For the Su-17 pilot, diving through a mountain pass at 500 knots, there was only a few seconds to visually acquire the target, align the laser rangefinder, and release the ordnance. When multiple colored smoke plumes appeared, or when ground coordinates were slightly miscalculated by an exhausted infantry commander, the fitter pilot had no technological safety net. They possessed no inertial navigation system advanced enough to pinpoint the error, and no targeting pod to zoom in on the troops below. They simply pressed the release button on the control stick and unleashed tons of high-explosive FAB-500 iron bombs. The results were often devastating. Friendly fire incidents, blue-on-blue engagements, became a horrific and regular occurrence. Soviet mechanized infantry and airborne troops repeatedly fell victim to their own close air support. This was not due to pilot incompetence. The pilots were highly trained and incredibly brave, flying a heavy, unforgiving aircraft through valleys lined with heavy machine guns and Stinger missiles. The fatal flaw was systemic. The aircraft was designed to treat the pilot as a passenger executing remote commands, and when that command loop broke down in the chaos of battle, the pilot was left holding the leash of a destructive machine with no eyes to aim it. So, after seeing how this rigid ground control doctrine actually performed in chaotic environments, do you think the Soviet design approach to the Su-17 was worth the trade-off in pilot autonomy? Let me know in the comments. The contrast with Western design philosophy during this same period is striking and illustrates the heavy price of the Soviet approach. Take the Sepakat Jaguar, a European strike fighter developed around the same time. The Jaguar was smaller and slower than the Fitter, and it carried a lighter payload. However, the Jaguar was equipped with a sophisticated inertial navigation and attack system NAVWAS. A Jaguar pilot could program multiple target waypoints into the computer before takeoff. Once in the air, the aircraft knew exactly where it was at all times, without relying on external radio beacons. The Jaguar pilot could fly low beneath radar coverage, completely disconnected from ground control, pop up over a ridge, and drop bombs precisely on a pre-planned coordinate based entirely on internal calculations. The pilot owned the tactical picture. The aircraft was an extension of the pilot's situational awareness. In the Su-17, the aircraft was an extension of the ground controller's situational awareness, and the pilot was merely the biological mechanism required to keep the airframe from crashing into the Earth. Despite these severe doctrinal limitations, the Su-17 airframe itself was continuously refined. The Sukhoi Bureau recognized the limitations of the early models and attempted to bolt on modern capabilities as the Cold War dragged on. This evolution culminated in the Su-17 M4, the definitive and most advanced variant of the Fitter family. The engineers made a massive conceptual shift with the M4. They realized that a low-level strike fighter was never actually going to fly at Mach 2. Flying at Mach 2 at low altitude generates so much aerodynamic friction that it melts the canopy and rapidly consumes fuel. Therefore, they permanently locked the translating shock cone in the nose. By fixing the cone in place, they limited the aircraft's top speed to Mach 1.7, but they saved a massive amount of weight by removing the complex hydraulic actuation systems inside the intake. They used this saved weight to install a significantly upgraded avionics package, the PRNK-54 Navigation and Attack Complex. This system finally gave the Su-17 a degree of internal autonomy, allowing for more accurate unguided bombing without relying entirely on continuous ground data links. The M4 also incorporated an internal television display in the cockpit. This was a critical addition, as it allowed the pilot to use the newly developed KH-25 and KH-29 series of air-to-ground missiles. These missiles were guided by a laser or a television seeker head. For the first time, a fitter pilot could lock onto a target from several miles away, fire the missile, and bank away, rather than having to dive directly through the enemy's air defense envelope to drop dumb bombs. Additionally, the M4 was heavily equipped with countermeasures, carrying massive chaff and flare dispensers strapped to the top of the fuselage to defend against the growing threat of infrared-guided man-portable air defense systems man-pads. Yet, even with the M4 upgrades, the fundamental DNA of the fitter remained unchanged. It was still a heavy, brute-force machine that lacked the sensor integration of its Western counterparts. This became glaringly apparent on the export market. The Soviet Union exported downgraded versions of the Su-17, designated the Su-20 and Su-22, to dozens of allied nations across the Middle East, Africa, and South America. In the hands of export clients, the fitter's reliance on ground control proved catastrophic. During the 1981 Gulf of Sidra incident, 2 Libyan Su-22 fitters engaged 2 American F-14 Tomcats. The Libyan pilots were acting under the direct orders of their ground control stations, which vectored them toward the American fighters. But because the Su-22s had no radar, the Libyan pilots had absolutely no idea they were merging with arguably the most capable air superiority fighters on the planet. The ground controller positioned the Su-22s for an attack, and one of the Libyan pilots managed to fire a crude K-13 infrared missile head-on at the F-14s. The missile was easily spoofed. The F-14 pilots, possessing massive situational awareness through their powerful AWG-9 radars, effortlessly maneuvered behind the heavy, sluggish Su-22s and neutralized them both with AIM-9 Sidewinder missiles. The Libyan pilots were tactically blind, sent into an engagement by a ground controller who fundamentally misunderstood the battle space geometry. The airframe performed exactly as it was designed to, but the doctrine sealed the fate of the pilots. The legacy of the Su-17 is a study in extreme contradictions. From an engineering standpoint, it was a triumph of pragmatic design. Sukhoi took an obsolete, underperforming swept-wing fighter and, by cleverly cutting the wings in half and adding a hinge, created a robust, hard-hitting strike platform that served for decades. It could absorb immense amounts of battle damage, operate from dirt strips, and deliver a massive payload of high explosives and cluster munitions. The AL-21 engine, despite its fuel consumption and sensitivity to airflow, provided the brutal thrust necessary to make the heavy airframe viable. Maintenance crews respected the fitter. Its systems, while heavy, were largely mechanical and easy to repair in austere conditions with basic tools. There were no fragile composite materials. It was built of heavy-gauge aluminum and steel, held together by thousands of prominent rivets. It was a frontline brawler. But as an instrument of war, the fitter was deeply flawed by the philosophy of its creators. The Soviet military establishment fundamentally distrusted the tactical initiative of the individual pilot. They believed that war could be scientifically managed from a central command post. By designing the Su-17 to function as a terminal node in a rigid communication network, they robbed the aircraft of flexibility. When the conflict was symmetrical and the communication links were pristine, the Su-17 was a terrifying weapon, capable of overwhelming enemy positions with sheer mass and speed. But combat is rarely symmetrical, and communication links are the first things to break under pressure. In the dusty valleys of Afghanistan and the chaotic airspace of the Middle East, the fitter pilot was constantly fighting two wars, one against the enemy on the ground and one against the blindness imposed upon them by their own cockpit. The ultimate paradox of the Su-17 is that it was an aircraft built to fly close to the Earth, down in the mud and the terrain, yet it was commanded by men staring at glowing screens in sterile bunkers far above the tactical reality. You can forge a Mach 1.7 titanium spear, pack it with thousands of pounds of explosives, and engineer a brilliant variable geometry wing to carry it into battle. But if the hand throwing that spear is disconnected from the eyes aiming it, the spear will hit whatever is in front of it, friend or foe. The fatal flaw of the fitter was never its hardware. It was the hubris of a command structure that believed chaos could be mathematically controlled. If you like this deep dive, leaving a like helps get it out to other military history fans. Thanks for being here.